he's not able to be here today. And then Andrew will come in.
Yeah, so
yeah.
Welcome to day 5.
Yeah.
We're into the home straight. So we have introduced you to the basic theory of epidemic models, both deterministic and stochastic, and we've seen how what those models tell us about the mechanisms and action of vaccination for the control of infectious disease. You're going to make a informed decision on policy. There's two things we haven't talked about which really are essential, and that's understanding the economic evaluation and the practical effects of how vaccines work, but also most importantly, how we can calibrate and fit our models to data to make them not just reflections of model world, but the real world as well. So TJ McKinley is going to take us into the full, robust world of Bayesian inference later, but as a bridge, we're going to start by hearing about some of the most basic fundamental methods we can use just to ground our models into reality, which comes down to how we can use models to estimate this quantity or not. So, thank you.
Thank you for the introduction. I think for the sake of time, I might start, or maybe give the 2 minutes, see if anyone comes in.
Let's just go.
Yes, let's go. So even for very simple models, which we have learned, like the SIR model, for instance, some of the quantities that we need to estimate them are really, we do not directly observe, and most of this will be around the transmission rate. How is the infection spreading? Which, for example, we can indirectly observe through case reports. Sometimes we do serologic surveys. These are surveys where, for some diseases, you can actually look at the IgG levels, and which can give you a history of past infection. And sometimes you even do contact tracing to just try gather what is happening in the background that you cannot directly observe. And we can then, if we do have some data, normally we can use some likelihood-based methods to estimate some of the unknown parameters. I'm sure TJ's session will delve more into some of the ways of linking data, estimating parameters from data, or linking the model to data. But these are really, you can say, the gold standard for model estimation. But for dynamic models, it can be hard to directly use these methods because sometimes you don't actually even know the proper form that the likelihood will take. So you cannot have an analytic formula for this. And they might be computationally intractable for very complex models. And I'm going to take you through some ways of estimating R0 from early phases of the epidemic using some simple statistical methods, not dynamic models, which can at least be tractable in terms of we can estimate them using some simple statistical models, like regression models, for instance. But if we can estimate R0 from initially from simple methods, we are able to at least even inform some of the more complex model with this quick and rough estimates of R naught. So that's the importance of having a handle of something as important as R naught early on before you have the full power to estimate them within dynamic models. And just as a reminder, in a simple SIR model, it's just a function of beta, which is the transmission multiplied by the duration of infectiousness, or the rate of movement from I to R. In a situation where you have more than one group, then betas can be several, and there's a formula there. We've also learned that you can also estimate R naught from the next generation matrix, which is really through getting the eigen values and eigenvector and getting the maximum of values in your eigenvector. R naught is really an expectation, which is the number of people that you expect an infected individual to contribute in a secondary manner in a completely susceptible population. So it should not depend on a model. But because we're estimating it from models, when we estimate R naught, they can be different according to the model we use, but essentially it's supposed to be model independent here. And this can be affected by whatever model we choose and how well it matches reality, the R naught that we estimate, or how far the statistical model we use to estimate the R naught is with the dynamic model that's actually underlying the cases or the data that we are observing. So I'll use this simple case. It's an outbreak in a boarding school. It's a closed population because it's a boarding school with a population of about 300 people. An outbreak of an influenza-like, if you call it, illness. I'm calling here outfluenza. And the graph on your right gives the daily number of cases of outfluenza in that particular school over time. I think this is over about 2 months, starting in on around March of 2019 to May. And the peak number of cases in a day was around 70. One way, if you are in a closed population, to estimate R naught is to use its link to the final size of the epidemic. And this formula gives a quick way to estimate R naught in that particular case, where ZF is really the final proportion that gets infected in that particular epidemic. So if you have R naught of final sizes, so you're able to read off. So this function plotted over a series of R naught will take this form. And if you have, for a particular disease, if you know it's a closed population and you can tell some final size of the epidemic, you can read the R naught or vice versa through this function. Who can try and tell why the function is almost at 0 before it starts increasing? Just a quick reminder. Anyone wants to try? Yeah, you do.
Okay, so I'm thinking it's a closed population. have a lot of susceptibles to manipulation.
Just look at the relation. What's on your x-axis? R naught, yeah. So, what do you know about the relation or the value of R naught and how the epidemic can pick off?
It's still less than 1.
Because R naught measures the spread
Mm-hmm.
of the disease. If R naught is increasing, then it means that the disease is spreading widely and affecting a lot more people. So the curve will go, because the proportions will be higher. The proportions of those who are infected will be higher as R naught increases.
Yeah, and is there some threshold to this? Yeah, okay. So you remember about when R naught is 1 or R effective is 1 versus when it's larger than 1 and how that impacts on the size or whether the epidemic takes off, yeah. Okay, it's just related to that. We can take advantage of the fact that initially during the epidemic, the increase in the number of cases has an exponential form, and use that to calculate, estimate R naught early on in an epidemic. And yeah, if the cases are increasing exponentially, then this will really be the formula. So the infected number of people at any time depends on the number initially infected and some rate there of infection that is constant over time, because we're assuming an exponential distribution. And that rate, that exponential rate, can be linked roughly with R naught and the duration of infectiousness of that disease if it is known. If you were to solve this particular equation, if you transform both sides, just based on log rules, this becomes log of the initial number of susceptibles, and that you can make constant. It does not depend on time. And then this becomes really a linear equation. So the log of the number of infected over time can really be a linear function with a constant and the rate of growth, that rate of exponential growth and time. So you're able to, if you're able to estimate that rate, then you can come back here, yeah? If you know the left-hand side of this equation, I need a pointer somehow. If you know the left-hand side of this equation, if you can estimate this through some regression, you're able to, and you know the duration of infectiousness, you're able to estimate R naught. And because this relationship is linear, it's easy to estimate through a regression model. And back to our data, if you, for example, take the first phase, maybe up to on the right-hand side, this is the first 2 weeks of data, and you just do a linear regression of those cases and time, you estimate an exponential rate of about 0.3, and if you plug that back into the relation between that rate and R naught, you obtain an R naught of about 2.8. This data is actually simulated, and it was simulated with an R naught of 2.5 with a duration of infectiousness of about 5 days. You can see you're getting a closer sort of estimate on R naught via very simple statistical model.
Sorry, I just want to see if I understand this.
Yeah.
They started by estimating or assuming the R naught was 2.5 to calculate the R naught of 2.82.
No. So the data, this epidemic, we know the underlying R naught in it because we've generated it from the computer with an R naught of 2.5 and a duration of infectiousness of 2.5 of 5 days. So we already know the R naught that has generated the data. But we are trying to see whether our method, which is a quick statistical model based on using the initial exponential phase of this, can reproduce the 2.5. Yeah. So sometimes you can also, instead of regressing on the log of infected cases, you can regress on the log of cumulative cases. And that is main, because when you accumulate, then you reduce the noise in the data. If you can compare this particular plot here, there can be a lot of noise around this, and when you want to kill that noise, sometimes you do some cumulative incidents and still use the same method to estimate R naught. And when you do that, you get rate, the exponential rate that is tight. If you compare these confidence interval here versus here. Yeah, but you might also bias the R naught to some level comparing those two. But these are sometimes some of the quick estimates quick ways you can use. Yeah.
So is there a way for you to, is there like a test which you can run if 3.5 is closer to 2.5? Like if you take the two R naughts, like which one is better? And I mean, obviously using your eyes, you can see that the other one is smaller and this one is bigger. But is there a way in determining which one is better? Because obviously this one has tighter confidence intervals than the previous one. Yeah.
Which I would argue is misleading.
You what?
I'd argue that that's actually misleading.
Okay.
And that's a problem with doing this. So if you, the Nicky and White textbook recommends using cumulative cases, and it's something you'll see in the literature.
Yeah.
And it has this nice property that you get a tighter estimate, and it deals with the noise. But in this case, and just for this simulation, it's seriously biased the estimate, while also reducing your estimate of the uncertainty. So it's probably not a good idea to use this method. In practice, what you have to do is test that you actually have an exponential growth. So the sort of test that you'd use for linearity,
Yeah.
you could use to test your method. There are packages in R which will help you to do this. But to be honest, if you really wanted to do this in anger, you should use one of the other methods, which is effectively measuring the exponential growth, but are more statistically robust with this. But this is the principle by which we do early.
Yeah. But I'll show you some of the packages you can use that have slightly better assumptions within the.
Is there a method of estimating how many weeks is early or how many days is early?
we can discuss that a bit. So identifying the exponential phase. So if something is exponential, it's growing exponentially, and you log transform it, then you come back to a linear sort of scale. I think that's clear for everyone. So if, for example, you log transform the cumulative cases and they were increasing exponentially, then you expect that if you plot that with time, it should be straight line relationship. Yeah. But if you pick too many cases, yeah, during like a huge chunk of time or too little, you might end up picking a phase that is not yet properly characterizing an exponential or not yet exponential, which means you might overestimate or underestimate your R naught. Why would picking too many time points underestimate R naught? Does anyone want to try? Think about how the think about how the epidemic is growing. It starts on an exponential phase. Does anything cull that growth down?
Oh yeah, you get to your peak, or you get to cases start to slow down.
Mm-hmm.
So you may combine a phase where the cases were rapidly growing with a phase which they were sort of slowing down. So that will underestimate the R naught.
Yeah, so if you pick a very wide sort of range in time, you might pick a phase that is not exponential, meaning, yeah, it's actually plateauing, yeah, because the susceptibles are being depleted in the population over time. You know, initially you have, you can assume the proportion who are susceptible is as good as the full population, yeah, meaning it's not culled. So as you pick many time points, then you risk picking a phase that is not exponential. So if you keep doing for this particular example in our data here, the outfluenza data, if we kept picking, say, 100 cumulative cases, log transforming that, getting the rate, the slope, because the slope here is the rate of the exponential growth, that estimate, according to how much of the cumulative cases we pick, then you get that curve, yeah? Meaning early on when we pick a few, then we had very high estimates of that slope, and beyond, say, 800, then that slope starts to reduce, yeah? Meaning at these stages, the slope is quickly changing, yeah? If the slope is quickly changing, that's not really an exponential phase, because in an exponential situation, the rate is supposed to be constant. And later, when you're looking at over 800, say, cumulative cases, then there's a very big change here. It's supposed to be more sort of flat, the flat region. And if you look at the residual error by the number of cumulative cases, you'll see it's higher at both tips. Okay, so that's just one way you can try and decide, am I in an exponential phase or not? Now let's look at another data set. This is a data set that is generated by an R naught of 0. It's an SEIR model. So we have the time people spend roughly 5 days in the exposed state, and then about, again, 5 days in the infectious state. So that generates this epidemic shown on the left with an early phase of it on the right. This is just a snippet of the tail of the first plot. So let's fit a regression line on those cases, log I, this particular equation I've showed here. Where is that? Yeah. So we're basically fitting this to that early phase of the epidemic and estimating the exponential rate here. And we get that to be about 0.11. When you use our earlier R naught formula, we plug in that, you get an R naught of roughly 1.5. But we know it should be 2.5. Why is that? Does anyone want to make a guess? What are we missing? No? I'll
Is this
tell
using
you.
the cumulative case method?
No.
That's
No.
a different thing.
Yeah.
There's something different here,
Yeah.
which is affecting.
Mm.
It's the reason why we're getting too low on it.
It feels like at the beginning there are very few cases in the sparse part, and that's maybe reducing the estimation because the number of people that are affected at the beginning, like from that very first week to when the curve actually starts rising, there are a lot of gaps in between.
Mm-hmm.
So it's difficult for you to estimate the true exponential.
That's a factor.
Yeah.
There's a reason there's those gaps here, but there wasn't with the other fictitious disease.
Yeah.
Is it like because of the exposed class?
In the right direction,
An
yeah.
additional, because we have more than one infective class.
Mm-hmm. Yeah, finish your thoughts.
You're there. What,
You're almost there.
having an exposed class, how is that going to change the rate of exponential growth? Is it going to affect it at all, or is it going to speed it up, or is it going to slow
Slow it
it down?
down.
Which disease was this?
Just influenza. Call it influenza.
Yeah. I didn't want to use real disease.
Real disease, so I'm
it's
calling it
highlighting that
outfluenza.
this is vague.
Yeah.
So this is
Yeah.
vague O's,
Vague.
which is certainly
Yeah.
not smallpox.
Mm.
It'll slow it.
It will slow it. So adding an additional delay in the rate. Okay. Yeah.
Because it just takes that extra time period to accumulate each generation of cases. So
Good. That's why you end up with a smaller rate there, and then which impacts on the R naught if you directly substitute that in the formula for R naught. So when we shift the model and we now have an exposure class on it, then we need to factor that in R naught, so that we take care of that extra delay. And this then should become the R naught that you use when you have an additional level. And when we do that, we substitute the same value, but the R naught formula now has two components. The first component is for the infectious, and the second component is for exposed. And you're able to get back like an unbiased R naught. So basically what we're saying here is the estimates of R naught are model dependent when we use models, and with each different model, you need to use a different formulation of R naught. There are some general ways that you can form these functions. If you know the moment generating function of some of this, you can look at work by, which I quote there, by Wallinger, Lipsich, and Vinicki and White, to just, yes?
I haven't seen the answer.
These, gamma, or this, or this, no, or R squared for, no, yeah, every regression model will have an R squared, but I didn't mention that because it wasn't the focus of the talk. Yeah, but when you do the regression, obviously you will have an R squared, which will be the amount of variation in the log of the infected people that can be explained by actually time at that point.
So if you want to check it out,
Yeah.
there is a practical which is based on these fictitious epidemics, and you can go through the procedure yourself.
Yeah.
The R squared, as you bring up, could be a good way of actually checking. The model checking is the essential thing you're going to do. This in practice, if you've got a terrible R squared, you're not going to trust that exponential growth or that use it for an estimate of R naught. So those sort of diagnostics would be a good way of choosing, in practice, if you're using these in anger, what time period you would use for your regression.
Okay, so yeah, I thought you saw this as an R in that slide.
There's a lot of R's going on.
Yeah. So this is just to signify a different type of SIR model where the time to event, the distribution of the time is not exponential, meaning not constant. For example, in some situations, you might have, you can divide your I state into two stages, yeah? So instead of saying SIR, you have S, I1, I2, then R, for instance, yeah? Meaning, and if each transition in the different I's have the same constant time, overall, you can introduce a different distribution by just splitting that in the time. So it might not. So that means it doesn't have to be exponential. You can have a delayed distribution by just using that fix. So when you don't want to assume exponential times, delay times.
And in fact,
Yeah.
that horrible gamma
Yeah.
distribution is the more realistic choice.
Yeah.
And if you, a lot of this work was motivated by the fact that people had been merely using the first equation to estimate R naught and getting it completely wrong. So understanding the serial interval is the key.
So I think there are some packages out there that you can read, learn, and use for this work. There is earlier, for instance, which uses the early phase of the epidemic to estimate an R naught. But I think for earlier, you must tell it to some extent the distribution of the serial interval, I think. There are some based on renewal equations or trajectory matching, which you can install in R and just see how it works. Maybe if you get time, you can do this in your practical session. The practical for this session is optional, I think. Yeah, but they're there in your practical sessions. But we've looked at a situation where the disease is just picking off. What are situations? What about situations where the disease is already endemic in the population? In which cases you might need a bit more information that I present there, like age patterns, household data, but we'll go through it as I go on. So the first, one of the quick and dirty ways, if a disease is already endemic, of estimating R naught is to use age at first infection and the life expectancy mean life expectancy in that population. And this is roughly intuitive. I don't know if I can quickly might not be properly. Yeah. So at an endemic steady state, remember the effective R naught is 1. It's not changing, and it's 1. Yeah. So if you call this an effective R naught, and it's not changing, and we know that an effective R naught is also an effective R is a function of R naught, and this is a proportion susceptible, yeah, in the population, yeah. And in an endemic state, the proportion susceptible is roughly the amount of time that you spend being susceptible on average. Yeah. So basically, it is the area, yeah, and it is a left area, yeah. The area under curve here would be the total time spent in your lifetime, and the area under curve under this session is the total amount of time spent susceptible. So you can just say this X star is basically A over L. Is it? Yes, yeah. So if you substitute it back, you will have 1 is equal to AL R naught. So if you make R naught the subject, then you get back roughly here, yeah.
Can you switch the screen back?
Oh, yeah.
Can't see with this thing.
Yeah, so You can also roughly estimate force of infection from catalytic models. If you can, for instance, have some serological surveys over time, but there's a link between also the force of infection and age at first infection. Yeah, so the age at first infection is really the inverse of the force of infection. So if you know the life expectancy, and you can have some data that can give you age at first infection, then yeah, you can get your rough R0 there using catalytic models, for instance. And what they characterize is a proportion susceptible over time and age here intersect in a catalytic model, because we follow people from birth. And serological surveys will give you the proportion immune, which you can just easily convert into proportion susceptible. And really, I think this is just saying that if you have proportion immune at 2 different time points, you can calculate the force of infection for each age group, for each time period. And I'll give you that with an example of rubella data in 1984 in the UK. The x-axis there shows a proportion seropositive for rubella IgG, I think, and age. And the right-hand side basically is what the force of infection function looks like for rubella by age group. Then the question is, how do you calculate the proportion susceptible in that setup? So you will divide the population into, you will divide the time points into small chunks for which you think the force of infection within each is constant, and then use the properties of the catalytic model in each of those spaces, because within each of those spaces the force of infection is constant. And the formula here gives the proportion susceptible at each age. In the first band, between age 0 and 1, it's simply the force of infection, the first force of infection. But in the second band, because the force of infection is different, you take the proportion, the first element here. This is basically the proportion susceptible from the previous age group, and then you decay that by the force of infection in the age group that you're interested in. So that can give you, you can still have proportion susceptible in such a model, even when that force of infection is changing with age. And we can relate that proportion to obtain a force of infection in a catalytic model. basically by solving this, making lambda the subject in this equation that we've already obtained here.
Excuse me? So the force of infection is the same within the small rectangle, but different between the rectangles.
Between the rectangles.
It's different.
Yeah, but but for some diseases it might be the same all through age. It's different. So this was just giving an example where it might be different. Now, that's one way you can calculate a force of infection when you have serological data, catalytic model. Then you can use the force of infection to at least obtain age at first infection and roughly get R0 from that. Yeah. In a situation where you can, the other way of in an endemic state is to use the next generation matrix, which we have discussed a bit in the class, and it's basically a product of the transmissibility and the infectiousness. Yeah, if you have several age groups in the population, then your beta actually is a matrix, and you have to factor in the proportion within each age group. So if we imagine beta times n in terms of matrix, what will that give you? If you do a matrix multiplication, the dark part, beta n, it will give you this part. If you multiply this part and this part is similar to just for the first row, you sum the product of beta 1. Yeah. So it's basically the total number of infections, transmission in that particular age, and then you just divide that, multiply that by duration. So it's basically K, the next generation matrix. If you can imagine it as a matrix that has components of R0, yeah, to some level. Because what's R0? Beta over gamma, yeah, if you recall. So you can use it to estimate R0 easily if you have the next generation matrix. And you can also estimate the force of infection to some level from the next generation matrix using this particular formula where gamma, no, this is phi, I think, is a proportion infected in each age group. Remember, the force of infection is beta times the proportion infected. Do you remember that? Yeah? Okay. But in if your beta is a matrix, if you multiply it with the proportion infected, and you want to solve for lambda, you'll have n equations in n unknowns, meaning it's not identifiable. So you have to restrict beta into a simple form. Now, before people started doing contact surveys, what people will do is, for example, assume different forms of beta, of the beta matrix. For example, this particular form means that people can only transmit within individuals of the same age group, yeah? Meaning you only have 4 distinct transmission rates. And with this, you're able to solve for the force of infection. You can also assume that transmission is only driven by children, for example. That's another form. No other transmission from other age groups, and many other forms. But now you really don't need to make those assumptions because there are many contact studies already around that you can use to layer a functional or a structure to your beta and estimate the force of infection. And this is what is done. So if you have a contact matrix, rate of contacts, and you know, for instance, the probability that a contact results in an infection, multiply that, you can easily have a data-driven next generation matrix and use it as a way of estimating the force of infection using this formula here, where K is really your transmission parameter, and then this difference in the bracket is basically the proportion of infections that happen between the ith age and the next age group. Yeah, because if you subtract the proportion susceptible today from the proportion who were susceptible yesterday, that is really the people who have been infected between those 2 time points or 2 age groups. So you can basically use the next generation matrix to also estimate a force of infection. In summary, there are many basic methods of estimating R naught. We've looked at the final epidemic size when you have a closed population. There's a direct formula linking R naught to the final epidemic size. You can use the early phase of the exponential growth in an epidemic with some simple statistical methods to also estimate R naught. In an endemic setup, and when you have the mean age at first infection, the only other thing you will need is basically the life expectancy, and you have a rough estimate of R naught. However, there are more advanced methods now that are already developed in packages that I've shown, and I would recommend you explore. And also using the largest eigenvector, if you have a contact study that you can use to estimate the next generation matrix, is also a good way to estimate R naught. Thank you. Any questions? We have 9 minutes. Yeah.
So if we can get the next generation matrix, can't I just continue and get the maximum eigenvalue?
Yes, yes. If you have the next generation matrix, and I think there's a practical in R, you don't even need to hand calculate it. In R, you can, there are functions to decompose it into eigen vectors and just get the maximum eigen value.
And I can put that for my R naught.
Yeah, and that will be your R naught. Any other question? Yes, yes, ask.
I was just going to ask which is the best method, but obviously, I mean, I know each of them has limitations, and then its good sides and bad
Mhm.
sides. So I think probably it's dependent on the model. I was just wondering which would be the best method.
Yeah, it's hard to answer that because it's also dependent on what information you have. Yeah. So because in a different, for example, in an early phase, and you want to estimate R naught, and it's a new disease, you don't have contact, you might be, and you I can't say the best is next generation metric because in that situation then you don't have anything. Then you might just be forced to use, for example, just wait a bit, observe how it's behaving, and just quickly use that method. Yeah. So it depends with the information you have, but if you have more really around contacts, etc., good for you because you'll be way better in terms. The amount of information you have will reflect in how good your R naught estimate will be.
And then, so for instance, like in most of these methods, you would have had to estimate certain parameters to, how can we be sure that what we are getting, or can we be sure that
Mhm.
whatever we are getting from observed data
Mhm.
is unique enough?
Unique enough to
Estimate the R, because in some of the methods we need beta
mhm.
transmission rate. In some of it we may need the there are different parameter values that we
Mhm.
need.
Mhm.
So how can we be sure that the observed data, or is there a way we can be sure that whatever parameter we are getting from observed data is identifiable? So this brings, like this,
I
I'm
think,
asking
yeah,
something about,
I think when you make these initial estimates, for example, of R naught, obviously, as the epidemic progresses, you people normally update as you get a bit more data, because if it's a new disease, people actually set up studies within epidemics to track or measure what, for example, their serial intervals are. So you can gather information, even during an epidemic, to try and update your past R naught estimates. Yeah, I think.
asking it
Or
I think you're asking two questions.
are there two questions? Yeah.
One is, are the parameters going to be identifiable?
Yeah.
And the answer to that normally is no. So you have to make judicious assumptions and approximations to decide what parameters you're just going to admit you don't know and you maybe do a sensitivity analysis on, and which ones you want to make an effort to try and estimate. Yeah, and fundamentally, some estimate of transmission is the first thing. It's the basic thing we need to progress, which is why we spend so much time talking about estimating or not, because it's a starting point. If we think of serology, the serology example there, you will always be able to estimate a single force of infection. However messy your serological data is, how incomplete, you'll be able to estimate one. If you've got more data, which shows that that's a poor fit, then you can then say, well, let's try and fit a functional form to that force of infection, or split it up into age groups. Yeah? The more data you have, the more potential you have to get a better understanding of what's going on. it's not just guided by the data we have, it is guided by the data we have. You know, that guides the complexity of the models that we can reasonably use, or I would argue that. Some people would disagree with me, they just say make up your parameters and hope for the best. But I think particularly if you're making policy decisions, the more grounded your model is in reality, the better. We could, in fact, we could easily do another course just on these issues, on just even one half of this lecture and the other half. The more information you have, the more potentially you can validate or cross-validate different sources of information. So if you've got time series and you've got cross-sectional data, you can do consistency checks that your estimates are the same from those different data sets. You can use more sophisticated methods called Bayesian evidence synthesis, where you use all of those available sources of data to feed into your model inference. That's something TJ could probably say a bit more about. Our colleague Danny DeAngelis does a lot of work in that area. Don't do it yourself. If you're thinking of that single epidemic, then so here we found out how the exponential growth rate gives us that first estimate, but it's going to be very uncertain because you've got the maximum effect of stochasticity in that early stage, but that's our first time to get an estimate that we can help to project. If you look at the studies which are trying to project what the value of R naught is and when an epidemic is going to peak, some really nice, John Edmonds from the London School does a really nice talk on this, where he shows how your uncertainty basically collapses to zero as soon as the epidemic peaks. Because for a single epidemic, once the epidemic peaks, you know what the herd immunity threshold is and you know what R naught is, but it's also game over in terms of prediction because it's already peaked. What's the model actually telling you? So, there's a race between the information you can gather for a single outbreak, the information you can gather before you get to that peak when you know everything. Subsets for that outbreak at least. For endemic disease, we've got different issues, but it's really just ground checking and making sure our models are consistent with the patterns that we see as a starting point. The slide that showed possible methods or better methods to use than these was a snapshot of what we now have available even publicly after COVID, because there's just so many different tools we can use for outbreaks and for serological data, cross-sectional data. But each of those would be their own course. So, in this course we're just giving the insight into these are the fundamentals of how we estimate, and there are good methods out there which should be your first port of call, which hopefully will map to the type of data you might have.
Just a follow-up question. Sorry from.
Yeah, sure, no problem.
So would you say that maybe a solution to that may be like to first of all check like the structural identifiability of the model itself, to be at least sure to an extent that parameter values can be more or less like basically unique maybe, but at least with the structure is if the structure is identifiable, then hopefully we can get something like
So
would we say that maybe a solution to possibly?
the most important thing to do when you are trying to fit a model to data is to first simulate some fake data and make sure you can recover the real parameters. Okay? It's amazing how many people don't do that, and even less people will write it up in a paper to show that it works. Part of the reason for that is often it's a bit shocking. So, we have fake data here to illustrate how badly it can go wrong, even when you know exactly the parameters. So, I couldn't agree more. Yeah, those sort of simulation studies are very important. They're very time consuming though, and they're difficult to justify when, you need a decision on this here.
Yeah, but a lot of identifiability issues can, if you're used to the art, you're able to think about them theoretically.
Yes, but
Yeah,
even now
yeah.
there are softwares that are
Mm.
able to
Yeah.
do that.
Mm. Okay, no further questions? Thank you.
No,
No,
just
oh.
so it's just clarification. Can we have a scenario where our node is below one and have an epidemic? Can I have such a situation? Apart from the equations, mathematically
You-
speaking.
On it will die out. So it will depend what define an epidemic to be. But when R naught is less than 1, depending on the stochasticity of the situation. Yeah.
So you might have seen in the
Yeah.
articles,
Yeah.
even when you have R not less than 1, you can sometimes see things that
Yeah.
you would classify as
An epidemic. Yeah.
And that's why, if you've got a new disease, like SARS, in the early stages, there's this panic about what is the R naught? Is it got potential to spread, or is it going to just die out? And some diseases can look like they have R naught greater than 1 when they don't. Yeah, Ebola is actually a really good example. We thought for decades that the community transmission, the community R naught for Ebola was always less than 1. And that you only could get transmission in hospitals or in very specific situations. And we were just wrong about that. Yeah, the R naught was always low, and we had been lucky that there hadn't been a wider outbreak. But the flip can also be true. You can have something which has got an R naught less than 1, will never spread widely, but can cause just a big outbreak or a scary outbreak just by chance, but will die out. It's really difficult. That's where stochasticity becomes, it's really challenging, teasing apart exactly what the potential is for spread at the early stages. And that's even before we talk about changes in behavior. Yeah, and again, that's a factor in Ebola, because the nature of Ebola, people's behavior changes when they know that there's Ebola in a way that it doesn't if you think, oh, there's flu, or even with SARS-CoV-2. Behavior changed initially, but then, it's not the same perceived risk.
So it's also true, I think, you can also have R naught greater than 1 with likely. It's possible.
Because R naught is not, it is for any disease. You see, it is a function of, it's an expectation of the number of secondary sort of cases. So if you now come to the real world, a disease can have an R naught of 2, 3, but it does not cause an epidemic, depending on many different things, including seeding, how put some light to this more. But on average, yeah, you would expect if there's proper seeding to the level that all the stochastic chances of it dying out without causing an outbreak are less than those in which it projects into an epidemic. Then you can say on average, yes, you would expect that a disease with an R naught bigger than 1 that is properly seeded will result in an epidemic. But it's not always the case.
Those variables here before you come up with your R.
Pardon?
I thought when you're doing modeling,
Mhm.
you need to consider all those other parameters, all those other variables before you come up with that value. Or in this case, you want to have it and then you consider other variables later.
No, I think this is a distinction now, yeah,
Because we have
between,
to
yeah.
move on to the next lecture. But
Yeah.
So if you want to calculate R naught from a complex model with lots of parameters, yes, you need to know all those parameters to estimate it. But R naught in itself, the definition, is not in any way dependent on the model. It's the expected number of new infections when you introduce one infected individual into a fully susceptible population. There's nothing there
About the
that says
model.
anything about
Yeah.
the model. Which means if we can use a simpler model, an approximation, maybe to a more mechanistic model to estimate R naught, that is entirely valid. So we can use it as a way of comparing between models as well. So it's like a lingua franca of modelling R naught, in that it allows us to make that comparison between models, but also it allows us to get that estimate without using the very complex model. So here we saw we can use a linear exponential approximation to estimate R naught for a fully dynamic model without fitting the fully dynamic model. We can use the catalytic model, which is another form of linear approximation, but looking at the age distributions in order to get an estimate, which can then feed into a more mechanistic model. Yeah. Okay, very quick.
Is there an established range of R naught, maybe in literature, that makes you say that if an infection is having an R naught ranging from 1 to 5, you say this is this, maybe from 5 to 10, this is another level? Is there an established range of predictions like that? Maybe in literature or something to guide?
Now, to guide on what, no, what we have in literature is really R naught estimated for different diseases, and you can say for something like measles, it's very high, yeah, but there's no guidance for
my
this is a
cynical
good or
answer
not, yeah.
would be everything's between 1 and 3, and if it's higher than that, it's probably measles.
Yeah.
Pretty much.
Yeah.
You know, most zoonotic infections are between 1 and 3. A lot of human infections are not much more than 5. Measles is really the exception.
Yeah.
With those literature estimates, that's assuming that the modelers agree that for the disease that they're looking at, they know where the R naught is. So yes, there are ranges. I would say also we're going to have an example of norovirus. That's an interesting one.
That's really interesting.
That's also
Yeah.
got higher on the zoonotic diseases. So if you've got something vector-borne, it gets very interesting how you define it. I would be cautious about looking at a range and saying, okay, I've estimated an R naught for my particular. The cases that I'm seeing, it's almost strange. It must be like this because there's lots of other factors behind that R naught. So generation time.
Okay, I think we're going to just crack on because we're a little behind. This lecture is going to be a little bit bitty. We're just going to wrap up a couple of extra bits of theory and aspects of the action of vaccines in populations that we haven't covered, and also point to how you can start to bring together all of these things, the modeling, the model calibration and fitting, to start to ask concrete questions about vaccine policy. And for that messy real-world stuff, I'm going to hand over Katie to talk about some norovirus modeling that we did a wee while ago now. But the other couple of things I'm going to talk to you about are not on the screen behind me yet. If we could switch over, that would be great. I'm going to talk about two things. The first thing is the little bit more exploration on what the consequences of the impact of vaccination has on transmission of infectious diseases, and then a little bit on how we can think more mechanistically about the action of different vaccines and how that matters and can be estimated during field evaluation. We're rebooting. I need rebooting as well, actually, to be honest. Have we got anything pendulum-like? No.
Maybe while we're rebooting. So TJ's kindly updated the folder with all of the lecture notes, and there's now some slides in there called further reading. So I've got some links to some books, some websites that might be interesting given some of the stuff that we covered in the course.
Yeah.
The other thing in there is a link to a couple of VIMC, the VIMC main website, as well as the link to apply for affiliate status. Now, everyone on this course, you should definitely apply for affiliate status. It's a really short form, and it basically kind of links you up with other potential mathematical modelers for infectious diseases. There's webinars, there's a buddy scheme we've got going on, and we've also got links to other bits of the VIMC website, and we've also got data viz tools if you're interested in some of the estimates from that side. So if you go to